We just finished the lecture content for this tutorial. The content for this tutorial, there are not many formula from the lecture. Instead, we have a lot of mathematical manipulations in our examples of problems. So let's try to address a problem. A triple bar linkage is connected as shown. Bar C is welded at the tips of bars A and B. So for those who have attended the industrial training in winter, you should know what is welded. If you didn't attend, let me tell you, it is just like you have a fixed end on those two bars, okay? So after welding, the material is very firmly attached on those two bars. It is not easy to remove it. At the temperature T0, the length of both bars A and B are L0. So this is L0. D0 equals to 1/2 of L0. The thermal expansion coefficients are alpha A and alpha B, where alpha A is less than alpha B. Assume material C has no thermal expansion effect, and the shear stresses on A, B, and C will cause negligible shear strain. That means we don't consider the bending of the material, we only consider the elongation or the axial deformation of the material. Part A. Neglect the direct stress caused by tension of C. Derive the angle of inclination of bar C for small size of data at the temperature T1. T1 equals to T0 plus delta T, where delta T is the change of temperature of the system. I don't know whether it is positive or negative, I just tell you it is delta T. And you have to show that theta, which is the angle of inclination, equals to tangent theta equals to sine theta. Notice that it is just the small angle approximation. For small theta, you have this approximation. And derive theta equals to 2 times alpha B minus alpha A times delta T. Besides, you have to prove the axial strain of bar C related to the thermal expansion coefficients and the temperature. The axial strain of bar C, which you are going to prove, equals to 2 of alpha B minus alpha A squared times the delta T squared divided by 1 minus the numerator. And you are going to find the direct and shear stresses in both A and B caused by the tension in bar C. For this case, approximate the small angle by this formula. Cosine theta equals to 1 minus 1/2 of theta squared for small angles. Besides, we are also going to consider the safety of this structure because I don't want the structure to be harmed. The safety factor of this bar, this linkage, is 1.6. Find the yield stress of this bar if the allowable temperature of this linkage is T1, which is under a change of temperature. Starting from problem 1, firstly we will find what is the length of A and B by using the change of length formula under the axial strain. For this part, we are going to neglect the direct stress caused by tension of C, so I assume there is no direct stress acting on tips of A and B, and we have to derive the angle of inclination of this bar. To do this, we try to consider the change of length formula under the thermal expansion as what we just mentioned. Delta T, which is the thermal deformation, equals to alpha delta T L. L is the original length, where alpha delta T is the thermal strain. Therefore, we can write LA, which is the length of A after the change of temperature, equals to the original length plus the thermal deformation. Similar for LB, it is the original length plus the thermal deformation, which equals to L0 plus alpha A L0 delta T, and for LB it is L0 plus alpha B L0 delta T. By those two equations, we can write the difference of length between bars A and B. Then by small angle approximation, we can find theta equals to sine theta equals to tangent theta. However, we can write tangent theta into LB minus LA divided by D0. Consider this right angle triangle. This is D0. Since this bar is inclined, the difference of length between LB and LA will be this opposite side. And then this is your theta. Therefore, tangent theta equals to LB minus LA divided by D0. Then you substitute this into here, and D0 equals to L0 divided by 2. Then you can show that theta equals to sine theta equals to tangent theta equals to 2 times alpha B minus alpha A times delta T. For part B, we are going to prove the axial strain. Part B is going to prove that the axial strain of the bar C. So we still consider this right angle triangle, D0 and theta. Then this side becomes D0 tangent theta, and the hypotenuse will become D0 divided by cosine theta. If we call this hypotenuse to be LC, then the axial strain of bar C equals to LC minus its original length. So it is the difference or the deformation caused by the change of temperature. It is deformation divided by its original length, which is D0 divided by cosine theta minus D0 over D0. Then you remove the cosine by multiplying both denominator and the numerator by cosine theta. Then you divide D0 from both denominator and the numerator to get this result. Then by small angle approximation, we find cosine theta equals to this. Finally, we do the substitution to prove the epsilon C formula. Next, we try to calculate the tensile stress and the tensile load in bar C. Notice that we have already got axial strain. Then we can find the tensile stress and tensile load by using the Young's modulus times the axial strain. So this entire piece of stuff is just the axial strain, epsilon C, and then we times it by EC, then it is done. Similarly, for PC, you just times the stress by the cross-sectional area, then you can find this piece of stuff. Basically, you just multiply AC to the stress. Consider at the tip of the bar A, we know for bar C there is a tension like this, right? For this tension, we decompose it into orthogonal components. For the component which is normal to the cross-section, it is the direct force. For the component which is parallel to the cross-section, it is the shear force. Then we can find what is the direct force and the shear force on it. For sine theta is what we did in part 1. It is 2 times alpha B minus alpha A times delta T. Then you put this stuff into the numerator to get the axial force or the direct force. After you get the direct force, then you can find the normal stress by using the direct force times the cross-sectional area, which looks like this. So you just divide the whole piece of thing by the cross-sectional area of A. By similar manner, for the shear force acting on bar A, it is just the axial force in bar C times cosine theta. So cosine theta is what we have found in this part. when deriving this formula. And then those two stuff are cancelled out. Then we can have the shear force in this form. Therefore, the shear stress is just the shear force divided by the cross-sectional area. At the tip of bar B, it is rather similar to bar A. One thing we have to change is just the cross-sectional area divided. So I just skip those steps and you can have a look by yourself. Now we consider the safety of this bar because we don't want to harm this bar. We don't want this bar to be permanently deformed by overwhelming load. Now we set the safety factor to be 1.6. Find the yield stress of bar A if the allowable temperature is T1. So what does that mean? First, we have to consider, since you have already allowed this temperature to occur, then there will be allowable stress generated by this temperature. Therefore, at T1, as what we just found in previous part, the allowable stress is in this form that we have already found in previous part. Let me show you. It is here. So now the allowable direct stress is in this form. Therefore, we can find the yield stress by using the safety factor formula, which is 1.6 times the entire piece. The result will become 3.2 alpha b minus alpha a squared times delta t squared divided by 1 minus 2 of alpha b minus alpha a squared delta t squared times EC. So in the exercise problems, I will try to make those quantities in numerical form such that you can calculate it yourself.